We're going to start off here with a video made by Scott Kennedy that really introduces proofs, because that's what we're getting into here, proofs. And this does a great job. It takes 4 minutes, but I think it's really well worth it. Here we go.
What is proof, and why is it so important in mathematics? Proofs provide a solid foundation for mathematicians, logicians, statisticians, economists, architects, engineers, and many others to build and test their theories on. And they're just plain awesome. Let me start at the beginning. I'll introduce you to a fellow named Euclid. As in, here's looking at Euclid. He lived in Greece about 2,300 years ago, and he is considered by many to be the father of geometry. So if you've been wondering where to send your geometry fan mail, Euclid of Alexandria is the guy to thank for proofs. Euclid is not really known for inventing or discovering a lot of mathematics, but he revolutionized the way in which it is written, presented, and thought about. Euclid set out to formalize mathematics by establishing the rules of the game. These rules of the game are called axioms. Once you have the rules, Euclid says you have to use them to prove what you think is true. If you can't, then your theorem or idea might be false. And if your theorem is false, then any theorems that come after it and use it might be false too. Like how one misplaced beam can bring down the whole house. So that's all that proofs are, using well-established rules to prove beyond a doubt that some theorem is true. Then you use those theorems, like blocks, to build mathematics. Let's check out an example. Say I want to prove that these two triangles are the same size and shape. In other words, they are congruent. Well, one way to do that is to write a proof that shows that all three sides of one triangle are congruent to all three sides of the other triangle. So how do we prove it? First, I'll write down what we know. We know that point M is the midpoint of AB. We also know that sides AC and BC are already congruent. Now let's see, what does the midpoint tell us? Luckily, I know the definition of midpoint. It is basically the point in the middle. What this means is that AM and BM are the same length since M is the exact middle of AB. In other words, the bottom side of each of our triangles are congruent. I'll put that as step 2. Great! So far I have 2 pairs of sides that are congruent. The last one is easy. The third side of the left triangle is CM. And the third side of the right triangle is, well, also CM. They share the same side. Of course it's congruent to itself. This is called the reflexive property. Everything is congruent to itself. I'll put this as step 3. Ta-da! You've just proven that all 3 sides of the left triangle are congruent to all 3 sides of the right triangle. Thus, the 2 triangles are congruent because of the side-side-side congruence theorem for triangles. When finished with a proof, I like to do what Euclid did. He marked the end of a proof with the letters QED. It's Latin for quod erat demonstrandum, which translates literally to what was to be proven. But I just think of it as, look what I just did! I can hear what you're thinking. Why should I study proofs? One reason is that they could allow you to win any argument. Abraham Lincoln, one of our nation's greatest leaders of all time, used to keep a copy of Euclid's Elements on his bedside table to keep his mind in shape. Another reason is you could make $1 million. You heard me. $1 million. That's the price that the Clay Mathematics Institute in Massachusetts is willing to pay anyone who proves one of the many unproven theories that it calls the Millennium Problems. A couple of these have been solved in the 90s and 2000s. But beyond money and arguments, proofs are everywhere. They underlie architecture, art, computer programming, and internet security. If no one understood or could generate a proof, we could not advance these essential parts of our world. Finally, we all know that the proof is in the pudding, and pudding is delicious. QED.
All right, so thanks to Scott Kennedy for that awesome animation. Goes through the whole history of the proof and why we use it and all that kind of stuff. You know, as he said, a proof is a convincing argument that uses deductive reasoning. Okay, we have to make statements and justify them. And to do that, we're going to need a whole bunch of properties. And we're going to start with our algebraic properties. The properties of algebra, which I know you've all been taught before in the past, and we solved the equations, and that's where we're going to focus. And the focus really isn't on the equation, but justification of each step. It's why we do what we're doing. And so hopefully by doing that, we're going to get through the process of writing a proof. And so to start off here, we're going to start with our properties from algebra. The first one is the addition property. All right, so if you're given like x minus 5 equals 12, we use the addition property to solve that equation. How do we do that? We add 5 to both sides. That's the addition property. So if you add something to both sides, or you add something to each side of the equation, that's using the addition property. Okay, so what else do we have? Well, we have the subtraction property, and we use that in equations like x plus 6 equals 15. You subtract 6 from each side. You have to ask yourself, how did you go from the equation on the top to the equation on the bottom? And that's what this whole section is about. Like, you have to justify this. How do they go from here to here? What do? They add 5 to each side, so that's the addition property. How do they go from here to here? And they subtract 6. That's how they do it. That's the subtraction property. Okay, next up, multiplication. And as you can probably guess, the division property. And these are of equality, but we're just going to shorten them up and write multiplication property. Like, how do you go from 1/5 x to x? Well, you multiply times 5. Okay, both sides times 5. Now, maybe you didn't know that one on the left. You should, okay, because you went through the algebra program. But the one on the right should give you a hint there. Times 5. And division property, divide each side by 2. Now, could you, in this step here, also say, hey, wait, that's the multiplication property? Somebody going, what? Multiplication? Yeah, multiply by half. You multiply by half, that goes down to x, and this side goes down to 4. Yes! Okay, so some of these can be used interchangeably if you can justify the reason. Like I had to tell you right there, you multiply by half. You just can't throw an answer down and be like, well, I think this one's right too. Okay, next one, substitution property. All right, we've used this in, what is it, section 8.2 back in algebra, substitution, where you have x's and y's, and they tell you x equals 5, so then you plug that x in. I'm probably telling you too much. I said I should let you look at these and try to figure it out. But look, we start with y equals 2x plus 2, and the only thing that changed was the x became a 5, and that's the other statement we have, and x equals 5. Okay, so if x equals 5, we can take the x out and put a 5 in. What's that called? What did they do? That's the substitution property. They substituted 5 in for x. All right, so that's our first batch of awesome properties that we're going to use. Uh-oh, there's too much there. Hold on, let's close it up so we can look. Next one, reflexive property. The reflexive property tells you exactly everything you already know. In other words, like if they give you something, you're always equal to yourself. That's the reflexive property. If they give you 30, then you know that 30 equals 30. If they give you x, then you know that x equals x. Are we going to use this a lot? Not till we get to the geometry part. It's going to be important in geometry when we have segments and things like that. But right now, here's what it's going to look like. They give you line segment AB. What can you conclude? AB is congruent to AB. Now, does that make sense to you now? Not so much. All right, that's for later. For later. Later. Oh, you didn't know I knew that, did you? Next property, symmetric property. Thanks to symmetry, where the left is the same as the right. Check this out. All you do is rewrite it. This is important. We're going to need this because sometimes if they say prove x equals 5 and you write, well, 5 is equal to x, all right, we want to turn that around. The reason we can do that, like everybody knows that, right? 5 equals x. Well, that means x equals 5. Well, how do you know that? That is the symmetric property. Okay, so that is another property we're going to use. Transitive property. This is like, some people call it like a chain rule. Basically says this: if A goes to B and B goes to C, then you can skip the B part. That's why it's called the chain rule. And then A will go right to C. All right, so how does that work here? If Y is equal to J and J is equal to negative 13, then you can conclude Y is equal to negative 13 and skip that whole J part. That's called the transitive property. It also works with like greater than, less than. If 10 is greater than 8 and 8 is greater than 1, then you can conclude what? 10 is greater than 1. But I get ahead of myself here. Distributive property, we know that. That's the fancy little 3 times x, 3 times negative 9 will give you negative 27. That's easy enough. Simplification. Okay, well, so if they give you like 3 times 4 minus 12, and you basically figure stuff out, this is figuring stuff out. figure stuff out. It's when you do calculations. All right, maybe you don't need to write that down. But see on this right-hand side, all we did was figure stuff out. We got a 0, and that's simplifying. We simplified it. What about combining like terms? Well, we know what that is. If they both have an x, you can put them together. 45x minus 20x, that gives you 25x. And the algebraic postulate, you always conclude, it doesn't matter what you're given, the coolness of the algebras is greater than the summation of the coolness of the world. That one's not yet proven. We don't know that one, but we're pretty confident it's true. All right, so we're going to start with some examples. We just have to tell the property that justifies each conclusion. So we're just practicing this. All right, so 6x plus 2 equals 12, and then they get, after that, they're concluding 6x equals 10. So what property allows us to go from 6x plus 2 equals 12 to 6x equals 10? What did they do to each side? They subtracted 2. That's the subtraction property. How cool is that? All right, how about number 2? If 45 equals x, then x equals 45. Do you remember? Okay, if you're not sure, let's go back. Let's go back. Which one of the... right there, symmetric property. There's a reason I had you write all these down, so that you learn that stuff. All right, so that's a symmetric property. How about number 3? What did they do here? 3x minus 7x equals 20, and then they concluded negative 4x equals 20. The 20s didn't change. What did they do here? They combined like terms. Okay, how about 4? Well, let me tell you. Most of the time when there's parentheses, not all the time, but most of the time when there's parentheses, then it's your good old-fashioned, what do they do? 4 times q, 4 times x. That's our good old friend, the distributive property. How about 5? If a equals r and r equals 60, then a equals 60. That is, if you forgot, it's right here. If you were given, there's a lot of scribble scrabble. All right, it's a transitive property. Now, let me just add another piece of information here. Maybe you looked at that and you're like, wait a second. A equals r and r equals 60. Well, I'm going to take out the r because r is equal to a, and I'm going to put in an a. And to me, that's not transitive, that's substitution. Well, you can do that too. In fact, on all of the algebraic, now it has to be these algebraic ones, and there are no inequalities, it's just equations and blah, blah, blah. But substitution property, okay, will work also. You could use either one. They'll both be correct. Hey, I'll give you a little happy face and a little thumbs up on that one. How about 6? All right, now 6... if B is the midpoint of GH, all right, so let's draw a picture. G, sometimes you need to draw a picture. H, and B is the midpoint. Well, what can I conclude? Look, I left some question marks. What? If then what? What do we know? What does midpoint mean? I mean, they're going to, if it's in the given is the part that they tell you is true. Now, if this is in the given, that's a midpoint, they're not telling you for no reason. They're telling you because there's a reason. You have to use that. What does the midpoint mean? The midpoint means it cuts it in half. Or GB, G line segment, GB is congruent to BH. Now I want to be technical here. Now I can say congruent, or I could have written GB equals BH. Remember, without the congruent, without the line over the top, it's the distance from G to B. Okay, so that's like a number, so they're equal. But if there's a line over the top, then we're talking about a segment, and segments aren't numbers. That's why they end up being congruent. But the moral of the story, what is our reason for knowing that? How did we know that? That they're the same, that this and this are congruent. How did we know that? Because that is what midpoint is. It divides it in half. Well, if that is what something is, then we say it's the definition of, in this case, it's the midpoint. All right, so in this case, we're going to say it's the definition of midpoint. Also be on the lookout for definition of bisector, definition of right angles, definition of supplementary. Everything that you know can show up in a proof. You just got to, it just depends on what they give you. So if you're not sure, check your definitions. It could be this, could be that. All right, so now we're getting to a 2-column proof. 2-column proofs are I like them. A lot of kids hate them, but we're trying to set you up here so that they're really easy. A 2-column proof lists all the statements on the left, and there's a justification on the right. Okay, so you put your statement here, it's on the left, your reason is on the right, they all have to match up. They have to give you some piece of information, okay, and that's what you're assuming is true. So this line here tells you everything that has been given to you. Given. Or everything that is known to be true. All right, they have to give you something to start the proof. Oops, my line sucks. All right, so they give you 45 plus 2 times blah, blah, blah. All right, now what they want you to prove comes in the second line here. Prove. All right, so they want you to prove that x equals 30. Now, I'm going to give you some hints. As you write these proofs, I'm going to be honest. Right now, I'm giving you the whole left-hand column. And that's great. If you don't want to worry about it till later, that's fine. But what you're going to eventually have to do is write this out by yourself. And so what we do every time is the given, whatever that is your first statement. Okay, if they give you 2 or 3 things, then you write it down in the first couple statements. And the reason, why can you state this? Why do you know it's true? Because it was given to you. Okay, so that's the given. So you can write the word given. That tells the reader that, oh, that was given to you. All right, that's right here. Okay, so the next line, now you have to go through each line and give a reason why they go from here to here next, and then from here to here to here to here. All right, so why do they go from statement number 1 to statement number 2? Well, if you look at it, what did they do? The only thing they did is they subtracted 45 from each side. All right, so that's our second reason. That's the subtraction property. And yes, we're going to write it all out. So then what happened? That's why this line is true. This goes with that. This justifies that. Reason number 2 justifies statement number 2. So then statement number 3, what did they do next? Well, it looks like they did the old distributive property. So that's what's going to go next. That's our reason for this statement here. It's the distributive property. I'm writing it out so that I'm making a point that you should write it all out. All right, then what happened? Well, then they added 20 to both sides, so we write the addition property. Addition property. Why do I always repeat myself I think that's a weird voice. Why do I use that weird voice? And then what do we do? Well, here's where I told you you could do, let's see, you can multiply by 1/2 or you could divide. It doesn't matter. You can use either reason here. Your teacher will be able to understand it as long as you do. Division property. I might ask my students, like, why did you write division property? Because I divided both sides by 2. Okay, you're good to go. Okay, why would you write multiplication property? Because I multiplied both sides by 1/2. It's the same thing. They're equivalent. But that's how you do a proof. Now look, here's another thing. See the last, what you're supposed to prove? That's the last thing right there. Bang, done. The reason why, division property from here, and then you're done with a proof. All right, so if I could write a book, Proofs for Dummies, the given statement goes first, and you always write given there. Those are free points. Your proof statement should be last, and there should be a step every single time and a reason why you did that. Okay, example number 2. I'm going to speed things up a bit. I did leave some of it blank because you need to start figuring out how to do this. Remember, the first statement you always make is whatever the given is. Now, they're giving you this big, ugly equation, 4x minus 2 times the quantity, 2 minus x, is equal to 4x minus 24. So the first reason you should always give is given. Okay, that's what the given is. And why don't you go through right now, pause the video, and write the reasons for steps 2, 3, and 4. Okay, pause the video, go! Okay, so hopefully you got these reasons. If you subtract 4x from each side, then you'll be left with negative 2 times the quantity, 2 minus x equals negative 24. They subtracted 4x from each side, so that's why we use the subtraction property. Then, now, most people would use the distributive property here. That's the way most students would solve this. I'm going to give you a hint, though. They didn't do it that way because that's not what's next. What's next? Well, they went from negative 24 down to 12. They divided by negative 2. Can you do that? Yes, you can do that. Gets rid of that thing. Or you can multiply by negative 1/2. That one's getting kind of complicated. But this works. They divided by negative 2. That's how they went from step 2 to step 3. I got to be honest. I threw that one at you to kind of keep you on your toes. Most people do distributive, but that's not what they did. They used the division property. And then they subtracted 2 from each side, so that's the subtraction property. And then you're left with negative x equals 10. What's the last statement you're going to make? Well, they want us to prove x equals negative 10. And if you divide each side by negative 1, what are you going to get? Divide by negative 1, you get x. divide by -1 equals -10. So that's going to be the division property. All right? So that's the second example. Pretty easy, right? You just write down the reasons why they do things. Well, all right, partner, let's do example 3, and we'll be all done here. Example 3, the first statement. We don't know the first statement. It's blank, Mr. Kelly. Oh, I remember from before. You always write the given statements first. And so we're going to write them both down under one line. You can use 2 lines if you want. Okay, but we're going to put both statements. If you look, we have 3x plus 4y equals 23, and we also have x equals 1. Now, why do we know that's true? Because they're given. All right, so that's the given statement. Number 2, 3 times 1 plus 4y equals 23. Where did they get that from? Well, I tell you what, if you're not sure, just go back. What does it look like? It looks like this statement right here. The only difference is there's a 1 in for x. Hey, wait a second, x equals 1. Plug a 1 in for x. What did they do? They substituted. That's substitution property. They just plugged in, for the x, they plugged a 1 in. All right, so that's easy enough. What about the next statement here? Well, here we go. They have 3 times 1. They just figured that out. Okay, remember when you just figure stuff out? What's that called? That's called simplification. All right, now some of you are going to be tempted to write multiplication property, but that's not the multiplication property. Don't do that. Okay, the reason why it's not the multiplication property is because you're not multiplying both sides. That's what the multiplication property says, that you can multiply both sides of an equation by any number and that your resulting equation is going to be equal to the first one. Okay, are we multiplying both sides of the equation? No. So therefore it's not the multiplication property, we're just simply simplifying. All right, so that should be simplification. Then we subtract 3 from each side, easy enough. And then, what do we write last? Well, you should always write whatever you have to prove last. So here it's y equals 5. How do you get that? You divide each side by 4, so we're using the division property. And you know what, boys and girls, that's it. All right, I know this video is a little bit longer because we had the introductory movie thing. Thanks again to Scott Kennedy for that. But hey, that's it. 12 properties. That's how many 12 properties you have to memorize. Put them in your brain. You got to put them up there in that there brain. And that's it. And that includes the Algebraic postulate, which, come on, let's be honest, that's common sense. All right, so learn all your properties, go through, do your practice, should be good to go. And then next lesson, we're going to do both sides. Uh-oh, a little tricky. Hey, this is Mr. Kelly from Baumholder. Remember, it's nice to be important, more important to be nice. So.